All right, today is going to be a lot of jumping around. We are going to start with the practice exam 3 things, because that has all the NMRs, and then I'm going to go back to practice exam 2.
I have to watch a lecture, and I'm feeling myself.
So if you pull up fall exam 3, I'm going to go through those NMRs and then move back to exam 2 and then go through those. So starting with this one here, I'm just going to do the top one. You can also do the bottom one that is over, that looks like an aldehyde, so that should be also doable. Taking a look at this NMR here, we have this peak, which is pretty clearly an OH based on its odd shape to it. We've got a CH2, another CH2. They both have 3 neighbors, or sorry, 2 neighboring, so they have 3 peaks. We have, what did I write this one as? 7 peaks for this CH here, and then these 2 CH3s. You can make up this 6H. On the exam, I would tell you how many peaks this is, just it's a little hard to see for this one. We've got 2 oxygens. Currently, one of them is an OH, which means that our other one, all things considered, is probably going to be a ketone. There are 1, 2, 3, 4, 5 signals or carbons, but we're supposed to have 6 carbons in the molecule, which means there's one that has nothing on it. We have 2 peaks in this 2 to 3 range, which is another sign of a ketone. We got 1 peak in the 3 to 4 range. That one's probably attached to our OH. And we can kind of use that to build our molecule. There's a question in the chat. How do you know when there is a 6-membered ring? So rings are a bit complicated. We're not going to really talk about those until a little bit later in the class. So for the moment, assume everything is not ring shaped. There might be some answers that are like benzenes. I'm going to tell you guys which ones those to cross out. So for this one here, there's 2 different places we can kind of start. We can have our OH is probably going to be attached to this one that's in the 3 to 4 range. So we can just kind of draw that out. As something we can use. We also have deduced that we have a ketone. The 2 things in the 2 to 3 range are a CH2 and a CH, so we can put that on either side. Our CH should have 6 neighbors, which would be our 2 symmetrical CH3s. Our CH2 is supposed to have 2 neighbors, which would be our other CH2 here, which is attached to this alcohol. Let's go through and assign them. So A, B, C, D, E here. A is our OH. B is our CH2 that's attached to our OH. That's in the 2 to 3 range. C is our CH2 that's attached to the carbonyl. D is our CH that is on the other side of our carbonyl. And E is our 2 symmetrical CH3s here. Okay, so I am going to leave this bottom one for you guys to do. Okay, bromine attached in 2 places. What is the formula for the one at the bottom? So this is C5H9OCl. Someone asked that looking 9Cl. Someone asked is when one of the practices is a compound that had 2 bromines attached to it, will there be a question like that on the exam too? It's fair game. Okay, so I'm gonna move on to practice exam 3.1. You can go ahead and cross out this top one. This is an aromatic ring. We're not gonna do this. Let's take a look at the bottom one here. Seems fuzzy. All right, we've got probably an OH based on the look of that. Got a peak between 9 and 10. This is going to be an aldehyde. And the rest of it, let's just kind of fill in like normal. So it's 2 peaks, 1 CH. It's got 6 peaks. Ooh, that looks like 7 for this CH. CH2 with 2 neighbors, and these 2 CH3s are basically going to be indistinguishable because they're both doublets, both in the same range. So we assign those are probably going to end up with the same letter or 2 letters that are good for both parts of this. Okay. Taking a look at this, we have 1 peak between 3 and 4. This is probably going to be attached to our OH. We have a peak between 2 and 3. This is going to be attached to our carbonyl. Usually like to start with the carbonyls. So let's draw out this aldehyde here. We said that the CH is between 2 and 3, so that one should be attached to it. It has 6 neighbors. Currently, it is next to the aldehyde, which has 1, which means that there will be a CH2 and a CH3 because we need 5 more. So that's one of our CH3s, a CH2 here. CH2 is supposed to have 2 neighbors. It currently has 1 from this CH. So it needs to be next to another CH here, which would leave us with this one, who is supposed to have 5 neighbors. It's also supposed to be attached to the OH. So you can put the OH on there and the CH3 on the other side. So I want to assign these A, B, C, D, E, F, and G. F and G are going to be identical. Let's start with A, which is the aldehyde. B is our alcohol. C should be our CH attached to the alcohol. D should be our CH attached to the carbonyl. It's in the 2 to 3 range. E is our only CH2. And F and G are the CH3s. All right, use that scrap paper. Taking a look at 3.2, crossing out the first one. This is also an aromatic ring. And I'll post these online so you guys can go through them if I'm going too quickly for you guys. We've got an oxygen and a Cl in this bottom molecule. We've got 6 carbons, but we have 1, 2, 3, 4, 5 peaks, which is a good sign. We probably have a ketone. There's also 2 peaks in this 2 to 3 range, 1 in the 3 to 4. 3 to 4 probably has our Cl on it. So let's just draw these out. CH2. 1, 2, 3, 4, 5, 6. So 2 peaks in this 2 to 3 range, 1 peak, 3 to 4. 3 to 4 most likely has our chlorine on it. The 2 peaks here are mostly a ketone. We also have an extra carbon, so that works for that. So we can start by drawing the ketone. Putting the CH3 and the CH on either side. Putting the CH3 on this side. Makes sense because it's supposed to have 0 neighbors, so being next to that carbonyl works. Our CH here is supposed to have 5 neighbors, currently has 0 from the carbonyl. So a CH2 and a CH3. Whoops, that should only have 1 slot to it. Because this CH has the chlorine on it, it's basically terminal. So if we were to stick the Cl on here, we wouldn't be able to keep going. This CH2 doesn't have anything on it, so it has an empty spot. It's supposed to have 3 neighbors. Currently has 1 from this CH here. So we could put another CH2 here, which has our Cl on it. And that would finish off this molecule. Let's do some assigning. So A, B, C, D, E here. A is going to be our CH2 with the Cl on it. B is our only CH, which is next to our carbonyl. C is our CH3 on the carbonyl. D is our CH2. And then E is our other CH3 here. Okay, so that's the NMR for this exam. We're gonna go through the rest of exam 2 now, and I'm gonna cross a bunch of things out. So let's do that. So I'm gonna do the fall 2020 exam 2. Flip these over. You can go ahead and cross out this entire aromatic, anti-aromatic paper here. We're just doing naming for ethers for this one. I'll go through some examples of that at the end, but you don't need to worry about this. This is going to be an exam 3 concept. Same thing with the NMRs. Don't do these. Taking a look at the reaction page, I think most of these are good. You guys can't do this one and this one here. Also, it's worth noting that anything we crossed out on the first exam is going to be on this exam because we went through and crossed out all the chapter 13 things. So it's probably a good idea to go back and review those. Okay. Next page. I think we're just crossing out this one. Taking a look at our synthesis. You can cross out the bottom one. You guys don't know how to do that one. And then the rest of it should be fine. And we'll go through an example of this when we're done. So let me go through the next one. So looking at 2.1, again, same concept, cross out all these NMR or these aromatic ones. Cross out the NMRs. I think this entire page is fine. Cross these three out, and I'll post this online if any of you guys are going too fast. You can cross out this synthesis problem, and then the rest of it's okay. Two point two, we're basically do the exact same thing. Cross out the aromatic page, cross out the. Yeah, I'll post which ones you guys should do for exam one, or actually just I'll relink it, and anything that was crossed out is ones that you guys should do. So I can repost those notes with this one. Rest of those should be fine. This bottom here. Okay, so let's take a look at this last page here where we're doing the Diels-Alder versus and the electrocyclic rearrangements. So for this chapter, there aren't a lot of mechanisms in it in general. So instead of doing mechanisms, we're going to do something like this. Because all the mechanisms are like one step, which is just an SN2. So let's take a look at this here. I'm going to walk completely through it. So we're supposed to draw all four hypothetical problems with the endo and the exo forms, and then use resonance to predict which one is going to be our major endo product here. So taking a look at this, we're doing a Diels-Alder. We can start with the 4 or 6-membered ring. With a double bond, this methyl here is going to be sp2, doesn't have any stereochemistry. Everything that's in the middle is going to get pushed upward. This OMe that's on the outside, and then this H would get pushed downward here. So let's draw those out. We have these two CH3s are going to get pushed up into wedges. This OMe is going to end up on a dash. That's our diene portion of it. So if we wanted to, we could draw this out 4 times to make life a little bit easier, because this part is never going to change. Okay, for our endo and our exo, so we're going to put a big plus minus for all these. Our endo is going to be where our carbonyl is going to come in from below. And I'll draw both the endos first. So the first one is where this is in the position it's currently in. The other would be where this is flipped over, and we put the carbonyl on the bottom and the methyl on the top here. Our exos are where it comes in from the top. So these would be instead wedges. And then same thing down here, except now they're flipped over. So these would be the 4 hypothetical products, which is the first part of this question. The next part is drawing resonance to decide which one of them is going to be our actual major product. So let's redraw these. For our diene here, we can have these electrons get pushed downward. Into our ring. Putting this negative at the bottom here. For our dienophile, the electrons can go upward. Putting our plus at the bottom here. Question in the chat. How do we tell which one is endo or exo? So the endo is always going to be where your dienophile is coming in from below. So they're going to be on dashes here versus on wedges here for the exo. Okay, so taking a look at these two resonance forms. Let's flip this guy over. Our one at the top here is going to be charge aligned versus this one at the bottom. It's going to be misaligned. Your negative is attacking your positive on the bottom here, or on the top here. The bottom one, the positive is in a different spot. So this top one where the OMe and the carbonyl are both at the top, which would be these ones, are going to lead to your major products. And then of those, your endo is always going to be your major. So this endo here would be your major product. Oh, I did that. Okay. So that would be this Diels-Alder question. I'm going to talk through some electrocyclic reactions before I do this one. So I'm going to pull out a scrap piece of paper. And I'm actually going to do a reaction from, let's see, where was that? I think it's on 1.2. Maybe it's in 2.1. Anyways, it's this one. We're supposed to identify if it's heat or light doing the reaction. So the first thing I'm going to talk about before I actually do this one is that something I see a lot on these exams is people will do this, where they will see that this kind of looks like a 6-membered ring, and they'll turn it into a 6-membered ring with a double bond. And this does not happen. For these reactions, you need to count your number of double bonds, and that's what's going to lead to your ring size. So even though this looks like a 6-membered ring here, we only have 2 double bonds, which means our cyclization is going to look like this and not like this here. So that's one thing to kind of watch out for. The other one is my advice for doing these problems here, where you have to figure out if it is supposed to be heat or light. The easiest way to do these is to just guess. And if you're wrong, it's gonna be the other one. So I'm just gonna say it's heat, and I'm gonna kind of do the work and see what I get. So if this was heat, I would draw 2 orbitals on top, 2 orbitals on bottom. These are both going inward. This one was on top. This one here was on bottom. When I do my rotations, to rotate the darkened area into the middle, I'm gonna go counterclockwise. Same thing for this bottom one. That would push this down, push this up, and I would get this product, which is wrong. That's not the one I want. That means it's light. There's only really 2 options here. You either have sin or anti. So if you do the work for heat and it gives you the wrong one, it's anti. If you do the work and it's correct, you have it right. So yeah, on this next one, so I'm gonna go back to over here. And this is where I want you guys to be able to draw these out and say if it's con-rotatory or dis-rotatory. So I'm gonna go through and do this one completely. And so this, because we're doing, this is basically a mechanism, you have to know the orbitals and you have to be able to say how it's rotating. So I'm gonna walk through this one. We have 1, 2, 3, 4 double bonds here, which means we're making an 8-membered ring, which we could start by just drawing that. We are gonna end up shifting. So this one's gonna go to there. It's gonna go to the top, middle, bottom. We are gonna have this isopropyl, this, where's the terbutyl coming off of? Here. And now we need to figure out these substituents here. So let's draw it out again and draw in our orbitals. We're using heat, so pairs of 2. First 2 are on top, second 2 are on bottom, next 2 are on top, last 2 are on bottom here. I'm going to isolate just the middle parts of this. So let me draw these in color. We have a methyl going in, another methyl going in, and then a propyl going out. Our top one is filled on this right, bottom one is filled at the bottom here. In order to get these to rotate towards the middle, this needs to rotate counterclockwise. This one is also rotating counterclockwise. They're rotating in the same direction, which is con-rotatory. It's going to push this methyl down, this propyl down, this methyl here up. And let's see, so methyl and propyl are going both downward. Other methyl is going up. And this would be a full answer for this question. if we look at the instructions, it was asking for orbital diagram as well as rotatory versus con-rotatory. So and for rotatory versus con-rotatory, I would just remember that to me, dis means opposite. So if it's not dis rotatory, they're not going the opposite way, they're going the same way, it's pretty con-rotatory. Or if you really want to remember it this way, I'm probably going to use the exact same wording. So this first one is the same, and the second one is opposite. What time is it? Oh yeah, so you could draw the enantiomer and get the same credit. You could also just put plus minus. We're not looking for one enantiomer versus the other. We're really just looking for like, are these two syn or are they anti to each other? Let's do some naming. Or no, I'm gonna do a synthesis problem first. I'll do it later. Okay. So synthesis problem. I'm going to do this one from 3.2. No, sorry, 2.2, not 3.2. We are, so if you read the instructions, this one says all carbon from the product must be derived from starting material given, which means we're going to have to make both halves of our Gibbs-Alder from this Br here, or this bromocyclopentane here. If I look at my final product, it's got two different 5-membered rings in it. Got this one here. Got this one here. Most likely this is going to come from something like this, doing a Diels-Alder, and then we'll do something to get the two BRs on there, probably BR2. So this should be a little bit more manageable looking at it. Our starting material, got to get to here and then get to here. So our first step is going to be, if we throw in throw in base, we can eliminate. We're already gonna have half of the molecule we want. So from here, we need to go from 1 double bond to 2. So putting in Br2 lets us dibrominate. And then large base can get us to our diene. Combining the diene and the dienophile. Can give us our Diels-Alder product. And then we want 2 BRs going anti, so we can throw in Br2. All right, I'm going to do some naming ones. Okay, so there's 2 ways to name this. You can either name this for the shorthand way, which is you're naming both sides of your ether. So this would be methyl propyl ether. Or you can name it as a substituent. If you're naming it as a substituent, you're going to use the larger chain as your parent chain. So 1, 2, 3 here. This is a propane. It's got a oxygen with 1 carbon off of it. So this would be a 1-methoxy propane. Let's draw something more complicated. And let's do this. So parent chain gonna be going right to left. It's a hexane. On carbon 2, we have an ether with 2 carbons to it, so this is an ethoxy. We've got a chlorine on 4, so 4-chloro. Doing some RNS. Our ethoxy is going to be our major group. 2, 3 here. This is going counterclockwise. So this should be S. Chloro would be 1. This side 2, 3. This is going to be R here. So if I'm naming this, this would be a 2S. 4R. C comes for E, so 4-chloro. 2 ethoxy. Why don't I put an L there? Hexane. What time is it? Okay. I might do some quick review of some of the stuff from chapter 13. So making ethers. Yeah, let's do terminal. We throw in something like NaO propyl here. This can do an SN2. And we can make an ether here. We could take this ether, throw in HBr, break it down. It's going to break on either end. Actually, to get back 1 equivalent of the starting material we got over here. So this left side should give us this butylbromine, and then we'll get propylbromine from the other side. Epoxides, which are maybe a little bit more complicated. Can be opened 2 different ways. So if we do this in basic conditions, this is going to open in the less sterically hindered center. Versus if we were to do this in acidic conditions. We would originally get the protonated version. Because it's protonated, it's going to be a little weaker on the more substituted position. It's going to open up in the opposite direction. And give us an OH here. Okay. There's a bunch of different nucleophiles you can do with these. They all follow the exact same rules. Same thing with like Grignards and LAH and things like that. Are there any questions from you guys? Or anyone in the chat? All right, well, if not, I am gonna let you guys go. I'll be on office hours in about 40 minutes. And I will see you guys on Wednesday. Oh, wait. Where did those?